All right, welcome to episode 28. So in this episode, we're going to revisit the display controller. So you may recall our goal was that we want to implement a 100 column by 37 row text mode using 800 by 600 SVGA graphics. All right, I'll start by reviewing where we were the last time we looked at the display controller, and I'll also explain why I haven't made a video about the 8-bit computer project in a little while. And the main focus of this episode is going to be discussing a new and better approach to implementing the display controller. So I've made substantial progress since the last time you saw it. And I'll go through a series of experiments that I did to get us closer to the point where we can display characters. And I guess this is a cliffhanger. Will we be successful? All right, let's see. All right, so the last time we looked at the display controller, we had data transfer from the host to the FPGA working, so we can send bytes of data from the host system to the display controller. We were able to place the received data in one of the FPGA's block RAM and also use that data to render pixels which appeared as ugly vertical lines on the display. So that was a good proof of concept to show that we could get data into the FPGA and use it for something. We ran into all kinds of timing issues because I don't understand FPGAs very well, and then we implemented, or at least proposed, a complicated scheme to use pipelining to separate the graphics pipeline, the processing of text characters, the rendering them as pixel data, and all that stuff. We had a complicated scheme to build a pipeline using block RAMs, and here's a little excerpt of the video where I described that scheme, and it all seemed pretty daunting. Alright, so I'd also like to address why I haven't made one of these videos in a little while. So I was teaching a summer course, so that certainly took up some of my time. Definitely it's summer, so I did lots of vacation and family stuff, and that's one of the really nice things about being in an academic position is having some flexibility in the summer for doing stuff like that. And I have to admit, I was definitely feeling unmotivated to work on this project, partially because it seemed like the complexity was getting out of control, and I didn't have a good handle on the technical details. Okay, but the good news is I thought of a much better approach that would allow me to make incremental progress. So let me tell you about that approach. So I think when solving any technical problem, a good way to start is to think, what is the simplest approach that could possibly work? So my idea is the FPGA will have an 8-bit register that contains the next 8 pixels to generate foregrounded background colors, and assuming that the data in that 8-bit register is always correct for the next 8 pixels, then by definition we get a valid display. So when thinking about the problem this way, we basically just have to work backwards and make sure that the correct data is in that register. And so this is sort of my big insight, and this is probably something that's very obvious to people who have experience with FPGAs, but I'm still pretty much of a newbie. So the idea is that if the design needs data, then the right way to have that data is to have already computed it on a previous clock cycle. So looking at the problem in this way, all I really needed to do is to build a parallel state machine or state machines that would make sure that the correct 8 pixels were always in that register. And the nice thing about this approach too is we always get some kind of image showing us what data is being produced and put in that register. And so that means we have a certain degree of observability that will help to figure out whether what we're doing is right or wrong. All right, so I ended up doing a total of 6 experiments. In experiment 1, I reset the core clock frequency of the FPGA to 40 megahertz, and I'll explain why in a moment. Experiment 2, we implement the 8-bit pixel register and use that to generate the foregrounded background pixels. Experiment 3, we implement a command protocol to provide a reasonably flexible way for the host system to send commands to the FPGA. Experiment 4, we use that command protocol to upload font data into one of the FPGA's block RAM. Actually, it uses several block RAMs. And then in experiments 5 and 6, we actually try to use the font data along with some character data to display characters on the screen. All right, so let me show you the results of each of these experiments. All right, before I go through the experiments, please be warned there is going to be some flashing video in here because there's going to be a VGA capture that will show you what the display controller is producing, so just be advised. All right, so here's our display controller circuit on the bench here, and the VGA capture here is showing you what it's outputting. So this is just basically exactly the same as the design from the previous episode. The only difference is that the FPGA core frequency was changed from about 80 megahertz to about 40 megahertz. And the only reason I did that is because I upgraded my FPGA development tools and it completely broke the design from working correctly at 80 megahertz. But in a way, that was not a bad thing, because if we are going to use pipelining to do our computation and pixel generation, we only need to produce a pixel every clock cycle at 40 megahertz. And as long as that pixel is completely ready to go, then there's no problem doing it at 40 megahertz. So this basically forced me to really do pipelining. All right, so all this design does is if you twiddle this potentiometer, the Arduino sends commands to the display controller, and the display controller puts them in a block RAM, and then the rendering is done from the data in that block RAM, and basically all it does is makes these ugly vertical lines, but that at least proves that data is going into the block RAM. Okay, so now our design, we know, works at 40 megahertz, so experiment 2 is going to be implementing that 8-bit pixel register and doing our pixel generation from that register. All right, so here in the experiment 2 Verilog code, you can see we have this register called pixreg, which is 8 bits, and we'll put 8 bits of data in there, and then the main pixel generation loop will use this. Every time it needs 8 pixels to generate, it will just grab it from this register. Right, so here we are in the pixel generation state loop, and basically every time we reach a point where we've generated the 7th pixel, it means that we're about to generate another block of 8 pixels, and we grab the contents of that pixreg register and put it in pixgen, and then the pixels are generated from pixgen. All right, so what this experiment actually does is, as I adjust this potentiometer, the Arduino will send bytes of data to the display controller, which in turn will put them into pixreg, and then they will get output on the display. So again, flashing video warning as I adjust the potentiometer here. Basically, every byte of data is then rendered as groups of 8 pixels on each line of the display, and so as I adjust the potentiometer, I get different values, and they are displayed. So anyway, what this experiment shows is that the basic strategy of putting 8 bits at a time into this register to generate 8 pixels at a time does fundamentally work as a video generation strategy. So for experiment 3, the main change was changing the state machine that processes bytes of data that are received from the FIFO that the host system uses to communicate with the FPGA. And the basic idea is that now the protocol is that the host system sends a single byte that is a command. So here are the command bytes that were defined for this version. And then, based on which command byte was received, the state machine goes into sort of a sub-state machine that is specific to the type of command that is being processed. So for example, if the pixdata command is received, then the command processing state machine is going to put the data associated with that command in the pixreg, and then the display will work basically as before. The pixel generation loop will take the byte of data that accompanied the command and use that to generate the pattern of pixels. So this particular experiment took me a really long time to get working, and the problem was that I just could not get the data byte associated with the command byte to be processed properly, and it took me a long time to figure out what was going on. But what I eventually figured out is that the Verilog module that I wrote that basically acted as a 1-byte FIFO, so that the state machine that took data from the command FIFO could notify the command processing state machine when a byte of data had been received. The control logic, the signaling that indicated when a byte was received, was not implemented correctly. There was a bug in it, and basically what would happen is that the state machine that processed the data that was in that 1 byte FIFO would see each byte of data twice. Basically, the signaling to let the consumer know when a byte of data was available was not correct and was flagging data as being available twice for each byte that was received. And so interestingly, the way I figured this out was by adding some debug LEDs. You can see them right here. So what the debug LEDs allowed me to do was, at a course level, see what state the command processing state machine was in, and I could see if it went into an invalid state, I would light up the red LED if that happened. But the other benefit is I could put oscilloscope probes on the anode of these LEDs, and now I can see traces on the oscilloscope that shows me exactly when the debug LEDs are being signaled. And so that basically gave me a lot of insight into what was going on at a very tight time scale. So here's a picture of the oscilloscope capture that allowed me to solve the problem. I had one of the probes hooked up to a debug LED that was telling me when the data processing loop thought it had received a byte from that 1 byte FIFO. And of course, what I noticed is that there were 2 pulses in a row for the same byte of data that was sent by the host system. And that, of course, meant that the loop that was trying to parse the received data bytes into commands and data couldn't properly distinguish the commands and the data. And of course, that was why the consumer of those commands wasn't interpreting them correctly. So I fixed the Verilog module that implemented that 1 byte FIFO, and once I did that, then everything started working. All right, so what this version of the design does is pretty much the same thing as what the previous one does. It takes bytes of data from the sent by the host system and displays them by putting them into pixreg, and then that gets used to generate the pixels. But the main difference here is that there are now proper command versus data bytes that are implementing the protocol that the host system uses to talk to the display controller. And that, of course, is going to be important because eventually we want to do things like have a variety of commands where you can upload font data, upload character data, modify other aspects of the internal state of the display controller. So this was a big step. It meant that I now had the infrastructure that was required to build a more sophisticated protocol between the host system and the display controller. So once I had a proper command protocol implemented where I could have data associated with each command, the next thing was to upload some font data into the block RAM of the FPGA. And so I found this nice website, int10h.org, that had a whole bunch of different IBM PC fonts. And the one that I chose was this what's it called? DOS ISO 8. I don't know how widely used this was, if it was ever used on an actual IBM hardware device, but it's a pretty nice font. What I liked about it is that it is single pixel vertical elements rather than the double pixel vertical elements, and in general looked pretty nice. So I was able to download it and convert it into a form that I could load into the Arduino sketch that is emulating the host system. All right, so here's the Arduino sketch, and you'll notice that there's this array of font data that's basically just the bytes that are encoded from that IBM PC ISO 8 font. And as part of the initialization procedure that the Arduino uses to initialize the display controller, it just sends each byte of font data to the display controller. And of course, before it sends the actual data, it sends the load font command to let the display controller know that it is receiving some font data. And I also have it sending some character data. So this is going to be the actual characters that are going to be displayed on the display, and those are sent separately. So what's interesting about this experiment, or perhaps not interesting about this experiment, is that honestly, I had no idea whether this data was actually arriving because I did not update the pixel generation loop to actually display any of this data. So what I could see is I just happened to use one of the I/O pins on the Arduino that happened to also be one of the ones that was connected to one of these LEDs on the Arduino, and I could actually see that data was being transferred. So I just kind of assumed that the FPGA design was still working, and in fact it did function as before, where I could twiddle the potentiometer and see the ugly vertical lines. So that was all working. I assumed that data was in the FPGA, so all that remained was to actually try to render some characters. So one additional aspect of experiment 4 that I couldn't really test fully was whether the font data and the character data would be placed in blockgram. So the way it's supposed to work is that you declare an array, and your synthesis tool notices that you have an array and puts it in blockram, because that's a more efficient type of resource for a memory than synthesizing an array of registers out of flip-flops. And so you'll notice here I have a comment, hopefully this gets inferred as blockram. And so I still had a question of whether or not the synthesis tool would infer that as blockram. And of course the answer is no. Alright, so here's the code for experiment 5, and as you can see, the font data is now instantiated as a Verilog module. And so, as it turns out, what you need to do to get the synthesis tool to infer blockram is you need to give it read and write signals and also read and write address buses. And basically you set up the Verilog module so that it looks like a RAM that has the kind of signaling that blockrams have. And then the synthesis tool figures out that what you want is a blockram and puts together one or more blockram units on the FPGA to instantiate your module. So here's the actual Verilog code for this FontRAM module, and it really couldn't be simpler. There's an array of data locations, 8-bit data locations, and on each positive edge of the clock, if the read signal is asserted, then we output the requested data on the output register, and if the write signal is asserted, then we store the incoming data in the appropriate location. And that's all that the synthesis tool needs to know that what we want is a blockram. Alright, so here is the core of experiment 5, which is the character generator process. And the basic idea is that if this ch needed flag register is set to true, that means that the character generator is being told to prepare 1 byte of pixel data based on the current character column and character row. And the main pixel generator loop attempts to maintain the ch call and ch row values to communicate to the character generator which character needs to be generated next. And once the pixel data is computed, so we compute the we figure out which character is being accessed in the character memory using the character row and character column. We get that character data, and then based on the character data and based on which row of the current character is being displayed, each character is 8 by 16, so there's 16 rows of 8 pixels forming each character. Based on which character is being displayed and which row of that character is being displayed, we construct an address into the font memory to figure out exactly which 8 pixels should be displayed for that row of the character that's being displayed. Once we get that data back from the font memory, we can then send that to the pixel generator. So the ch_pixel_data register, it's similar to pixreg. I just decided not to reuse pixreg so that the existing pixreg functionality would also work. But basically, this is what tells the pixel generator loop what block of 8 pixels needs to be generated for the character that should be displayed. All right, so here we can see in the VGA capture the output of this experiment, and it does indeed render character data. There are some aspects of it that aren't quite right. The first 2 columns of characters, first of all, are the wrong characters, and they are also mispositioned slightly. But when I saw this particular output for the first time, I was hard to find the words. I was really amazed that this worked, because it was the first time that I felt like, yes, I think we are actually going to get this display controller to work. So at this point, the only real work remaining was to fix the character placement issues, that the first 2 columns weren't right, and column 3 really should have been column 1, and there were some slight placement issues, but still, I could tell that we were getting close at this point. All right, if you look right here, you'll see a photo of a monitor showing the same image. And one of the things that you can see if you look closely is that the B and C characters in the first 2 columns are slightly in the wrong place. They are pushed down one row of pixels lower than they should be so that they don't line up with the other characters. So one of the things I wanted to fix in experiment 6 is to really get a handle on precisely positioning the pixels just where they needed to be to make the image perfect. So as I looked into the placement issues, I began to be concerned that the horizontal and vertical pixel counts in the visible region weren't accurately reflecting the places that the pixels being generated actually were appearing on the screen. So for example, I changed the pixel output process so that it used a particular color every time the vertical count was a multiple of 16, which means it should be at 0 and 16 and 32 and so forth. And rather than seeing that row of pixels right at the top of the screen being rendered in that color, it was actually at pixel row 15, I think. It was much further down. So there clearly was an issue where the horizontal and vertical counts weren't accurately being reflected. And there are a number of reasons that could happen. My conclusion was that it had something to do with the relative timing of the horizontal and vertical sync pulses compared to the pixel data. And so what I did is I implemented this test pattern. So this is experiment 6A, and it's simply a grid that highlights all of the pixels where the vertical count is a multiple of 16 and all of the pixels where the horizontal count is a multiple of 16. So you get squares. And I had to completely re-implement the horizontal and vertical sync generation to get everything to come out right. I don't know how well it is evident based on just this VGA capture, but when I looked at it on the monitor, it looked more or less exactly right. I think there may still be an issue where the first column of pixels is not actually being seen, and so we're only getting maybe 799 pixels in the horizontal visible region rather than 800, but nonetheless, it was very, very close. So that meant I could take this now trustworthy horizontal and vertical sync generation and basically backport it into the version of the design that tried to display characters. All right, so that finally brings us to experiment 6 that you can see here in the VGA capture. And what finally made it work more or less 100% was rewriting the character generator so that rather than relying on a process elsewhere in the system, specifically the pixel generation process, to compute the character row and character column that needs to be displayed next in the next block of 8 pixels, instead, I had the character generator compute that information on the fly. And basically what I found was it's very hard, or at least I was not able to get the pixel generation loop to accurately figure out which row and column of character data was needed next. You'd think that would be fairly simple, but it turned out to not ever work reliably. However, that information can be reliably determined from the horizontal pixel count and the vertical pixel count. So I won't go through this code in detail. You're certainly welcome to look at it on the website, but this turned out to be pretty easy to implement and basically worked 100% reliably. So so what you see here is the final result, and it shows, you can see I fixed another bug where it's supposed to print, or it's supposed to display 4 lines of text at a time. It was only displaying 2 lines of text at a time that happened to have identical data, so all the lines were the same. So now you'll notice that there's 2 lines of just characters with increasing character codes, and then 2 lines of meme text, and then that repeats. So anyway, yeah, this really is a valid text image, a valid text mode being displayed. Really, the only thing that is missing at this point is a proper full frame buffer that allows us to independently control every single character. And of course, we also need character attribute data so that we can get foreground and background colors, maybe selected from a palette. That will be the next project, but this is really, really good. This is basically a good text mode output, so very pleased with this progress. All right, so in conclusion, I think the design is in pretty good shape at this point. The character generation strategy seems to work pretty well. I think the pixel placement is either correct or very, very close to correct. So what will happen next is I need to implement the frame buffer in the SPRAM. That's the single-ported large RAM in the FPGA, and it's really the only RAM that's large enough to have all of the character and attribute data that we want to store. So that'll be the next step. So stay tuned, and I will see you in the next video.